now pioneering.
What does the future hold for our health? Longer lives, more clinicians, high-quality care. The power to help clinicians benefit from all the research data in the world. The power to take on the infodemic with trusted information and help millions of students become practice-ready professionals. We believe that knowledge has the power to shine a light into the darkness.
IBM Research is home to 3,000 scientists and researchers around the globe who deeply believe in the power of the scientific method to invent what's next for our company, for our clients, and for society. It would be impossible to tell the story of computing without IBM, and it would be equally impossible to understand the next computing revolution without the technologies that IBM Research is now pioneering.
Hello, I guess we're waiting for Markus.
Hi, yes.
Yes, he's been very, I've seen him in the conference and so forth, so he knows all the time zones and all of that. So he should be good.
I can see him.
Yeah.
Okay, I just sent him invitation.
Great.
And he's here.
Perfect. Welcome, Markus. Can you hear us?
I can see you have the camera and mic on, but we can't hear you. Check the microphone settings.
Yeah.
Yeah, you're good.
Now we have some sound, I guess, but it's not yet what I want.
Well, it sounds pretty good. You sound pretty clear.
Can always be clearer, but okay. Let's
Okay,
see.
this is better.
Now, yeah, this is better now, I guess. Yeah. Okay.
Would you like to check screen share?
Yes. Let me just.
Okay, I'll stop.
Figure out my screens and. Sorry.
No problem.
Am I?
You're in the same setting as your student earlier.
Yeah, he was kind enough to lend me his office. No, actually, it's the other way around. But it's a better room than the one he was in normally. So okay, let me try the screen share. Here we go. And now it allows me to share the whole desktop here. Okay,
Yep.
now you should see this the whole thing. And
Yes,
if you,
it's okay from my side.
is it okay? Does it look normal?
Yes. Try to next slide, just for double check.
Okay,
Yeah, good, good, good.
good.
Yep,
Okay.
looks great. Looks great.
Should I stop? Do you want to keep this? It looks the same as your background, but without the commercials.
The sponsor
I just
stuff.
take over the screen share.
Okay. Let's see. So I'm still sharing. Am I? Or did my sharing stop? Yeah, Zoom can only share one screen. Okay.
Yeah.
I see. Let me just close the blinds a bit. Too much.
What does the future hold for our health? Longer lives, more clinicians, high quality care. The power to help clinicians benefit from all the research data in the world. The power to take on the infodemic with trusted information and help millions of students become practice-ready professionals. We believe that knowledge has the power to shine a light into the darkness.
Light into darkness. Okay.
IBM Research is home to 3,000 scientists and researchers around the globe who deeply believe in the power of the scientific method to invent what's next for our company, for our clients, and for society. It would be impossible to tell the story of computing without IBM, and it would be equally impossible to understand the next computing revolution without the technologies that IBM Research is now pioneering.
So are we also live on YouTube, I wonder? Or that'll come later. Maybe check. Yeah, it seems we're on YouTube.
What does the future hold for our health? Longer lives, more clinicians, high quality care. The power to help clinicians benefit from all the research data in the world. The power to take on the infodemic with trusted information and help millions of students become practice-ready professionals. We believe that knowledge has the power to shine a light into the darkness.
IBM Research is home to 3,000 scientists and researchers around the globe who deeply believe in the power of the scientific method to invent what's next for our company, for our clients, and for society. It would be impossible to tell the story of computing without IBM, and it would be equally impossible to understand the next computing revolution without the technologies that IBM Research is now pioneering.
What does the future hold for our health? Longer lives, more clinicians, high-quality care. The power to help clinicians benefit from all the research data in the world. The power to take on the infodemic with trusted information and help millions of students become practice-ready professionals. We believe that knowledge has the power to shine a light into the darkness.
Okay, so Markus, how long do you think your talk would be roughly? You're aiming for around 40 minutes or so.
I think 50 is what I planned for. So
Okay.
I think this was the 60-minute session overall and 10 minutes questions. Well, if that's
Yeah,
all
sounds
right.
perfect.
Okay.
Yep, sounds perfect. So I'll take questions on chat and on Slack, and we'll round out the hour with the questions.
Great, thank you.
Just wanted to say hi, Markus.
Hi, Claudia.
Hey, Claudia. Okay, so for those waiting, we're going to wait
IBM
3 more
Research.
minutes, I guess, for more people to join.
Mhm.
IBM Research is home to 3,000 scientists and researchers around the globe who deeply believe in the power of the scientific method to invent what's next for our company, for our clients, and for society. It would be impossible to tell the story of computing without IBM, and it would be equally impossible to understand the next computing revolution without the technologies that IBM Research is now pioneering.
What does the future hold for our health? Longer lives, more clinicians, high-quality care. The power to help clinicians benefit from all the research data in the world. The power to take on the infodemic with trusted information and help millions of students become practice-ready professionals. We believe that knowledge has the power to shine a light into the darkness.
Okay, so let's start. So hope you had an interesting discussion in the poster and demo session on Gallertown, and welcome to the second keynote of ISWC. I'm honored to introduce the keynote speaker, Markus Krötzsch. Markus is a professor for knowledge-based systems at the Institute for Theoretical Computer Science of the Faculty of Computer Science at the Technical University of Dresden. So he conducted his PhD studies at KIT, which he completed in 2010, supervised by Rudi Studer. He later did a postdoc in the Department of Computer Science at the University of Oxford before moving to Dresden in 2013. So Markus has a long history of important contributions to our research community that span both kind of theoretical contributions as well as important practical and applied works. In terms of theoretical topics, he's published results in a wide range of problems relating to the topic of today's keynote, particularly description logics and rules. On the applied side, he's made significant contributions regarding semantic media wiki, various popular reasoning systems like ELK, and last but not least, you may have heard of a thing called Wikidata. Actually, if you look at Markus's Wikidata profile, it's a suspiciously detailed and well-referenced, so it was also a useful source for this introduction. So we could go on mentioning various contributions. Some other highlights would be being co-editor of the L2 standard, being co-author of the seminal textbook in our area, Foundations of Semantic Web Technologies, which perhaps some of you used in your studies. In summary, Markus has a long history of major contributions to our community, and thus it'll be very interesting to hear what he's going to talk about today. So his talk is entitled Data, Ontologies, Rules, and the Return of the Blank Node. And the last part is very interesting to me because Return of the Blank Node sort of invokes Return of the Jedi and Return of Kings and other such heroes, but there's also movies like Return of the Living Dead. So it'll be interesting to see which way this goes. So Markus, please.
Right. I'm going to share my screen first, which takes all my concentration to do. So I hope you can see now the right screen, the one which has a full screen version of my slides. Yeah, thank you very much for this flattering introduction and for the friendly overview of my humble contributions to one or the other things we did here. It's a great honor for me to be giving the keynote in this community, which in many senses has been the cradle of my own academic research path many years ago in 2005, when I started as a PhD student in Karlsruhe. Now, when we think of this community today, when we hear the term semantic web, of course, we have some mixed feelings to it, I guess. So looking back, we certainly have come a long way, which started with many fancy diagrams like this layer cake here and high-flying visions, but also involved linked open data, the ontology world, the description logics have been mentioned, and recently knowledge graphs as a new topic that unites many people here again. But overall, it's still kind of a mixed bag, and sometimes it's not completely clear what we currently are, whether we are now semantic web or should be knowledge graphs or something altogether different. Also, over the years, we have had many controversies in this space. I remember vivid discussions about data versus ontology, logic versus pragmatism, and bringing the web back into semantic web, and so on. So many of these discussions have been had, and sometimes it's not completely clear what we as a community stand for, other than, as a colleague recently said, being the community with the best parties at conferences, which is of course also something one can hopefully agree with. Unfortunately, not so much in the online format, I'm afraid. But besides this, besides having wonderful parties and being a nice community, I think that there are very many crucial insights that actually unite us, which are technical in nature, and which I think I only got to appreciate over the years when talking to other people from communities like databases, like logic, or practitioners, when I realized that they are not understanding many things that we understand and find completely natural. So a first thing I would like to mention in this respect is that for us, vocabulary has meaning. We always start from the vocabulary. When we see an IRI, it's not just a string, it's a concept which has some meaning behind it, which needs to be discussed and agreed upon. I remember vivid discussions at my first dub in 2006 in Edinburgh when people discussed about the HTTP response codes that we should send when returning RDF on the web. So these things matter to us because we know that they are important, that it's important to understand what the terms mean that we are talking about. And this is the same no matter whether you're in linked open data or an ontology. The reason for this, of course, is that we want to share our knowledge, that we believe that knowledge is for sharing. There's this famous definition of ontologies as a formal, explicit specification of a shared conceptualization. And the shared here is of particular importance, I believe. Yeah, that somehow meaning, and this is what semantic in the end means, must somehow be meaning agreed upon between different human communities and different human stakeholders. This is also why we value declarativity and openness standards in general. Again, this is not the same for all communities you can imagine, and it's not always the same for example, for industry, that they want to share everything. And then as a third thing that I would like to mention here is that, yes, also being pedantic is okay in the semantic web. Yes, so we understand that if you want to go beyond social aspects and you want to really have technical systems that work, you have to be precise and you have to look at specifications, and it matters what the formal semantics is. And again, I think many camps of our community can agree on the fact that details are very important in order to make something technologically viable and robust. Okay, so all of these unite us, and I think we should keep that in mind. Now, on the other hand, there is one more thing, of course, the triple. And I'm not sure if I should mention this as something that unites us or that that divides us, because obviously the triple as a data structure, as an atomic component of all our information, is so central to the semantic web that it's hard to imagine anything without it. And obviously it has great advantages. Yes, it gives us uniformity and simplicity, easy to explain data model. It gives us scalability as well. Yes, so we can have full indexing in our graph store, 6-fold indexing. Try this with a database, which is relational. We have structural compatibility. We can take two data sets and merge them, and they are still a data set. And of course, it gives us this powerful graph metaphor that is so nice for explaining what we are about, even if we never use it in bigger practical examples because it doesn't scale so well. Okay, so this is all wonderful, but still the notion that everything should be triples has repeatedly been discussed in the past. And I think there are many good reasons for this, why it's not so obvious that we should have everything in triples. The main driving force for such criticism was usually the simple observation that the world is rather complex. Yes. So if you look at other communities that share data and that work with data, they often prefer less extreme forms of normalization. So normalization being the process of hacking some kind of data schema into a simple unified format, as we do. Relational databases don't do it quite as strongly. JSON, yeah, you have much more structure in a JSON document, and this might be one reason why it's a preferred exchange format for the web rather than RDF. OWL, Shackle, our own standards also routinely handle objects which are much more complex than single triples. In order to represent a single OWL axiom, you often need many triples that are quite complex. And even modern knowledge graphs, if you look at them, are not so simple after all, right? And when I say modern knowledge graphs, Aidan already has mentioned it, of course, something I think of immediately is Wikidata. Now, Wikidata, I think it needs not much of an introduction these days, thankfully. It's not that young anymore, actually. We are celebrating the 10th birthday of the project in a few days from now. So it's half the age of the semantic web in a certain sense. It's been around and people know it by now, I think. It's a free community-built knowledge base and still outstanding in this respect. I don't know of any comparable project which works in this way and has this scope. It has a large international community, which I think is its main asset, really. The community is what matters for such a project because it's about creating knowledge together. And as a side effect, it also has become quite large. Yeah? So people have entered a lot of data. Only last week, we have celebrated with some worries, maybe even when you think about scalability, the creation of the 100 millionth item in Wikidata, 100 million content pages, if you like, with many more properties and statements on them. If you turn everything into RDF, you currently get something which has about 14.2 billion triples. Yeah. And all of this has many uses, which you probably have heard about. It's in your phone. If you have a smart assistant in your car at home, it usually uses data from there. It has been used in many other special purpose applications in many countries because of this internationality. It's used also by many other data curation projects to refer to and to cross-connect their databases and to ensure that their quality is somehow improving and aligned with this. Okay. But as I said, it's complex. It's not so easy. It's not a simple knowledge graph consisting only of triples. And we can see this if we look at any of the pages. For example, here take Tim Berners-Lee, Q80 in Wikidata by utter coincidence. There you find some statements which look very normal to us. Tim Berners-Lee, instance of human, it's perfect triple, subject, predicate, object. But if you go further down the page, you also find things like Tim Berners-Lee, employer at CERN, with additional information here, start time, end time, and even the position that he held during that interval are given, not as information about Tim Berners-Lee, but as information about the statements that we have here. So there's something complex here going on. And similar things we have in many other forms here. We have an award which he received together with 4 other people. So we have 4 values for together with here. Okay. So this is what I mean with complexity in this sense. And of course, knowing RDF, we know how this can be handled. We can easily map this into triples. It might look roughly like the sketch given here. We just create a new node here in the center for each statement. And for example, connect Tim Berners-Lee to CERN through this extra node. And then the extra node can be used to add all kinds of additional information that we want to add. This is called reification, even if it doesn't use the RDF reification vocabulary. And it works in practice. Actually, this is what happens and what is done. Wikidata is a big user of semantic web technologies these days. It has official IRI mappings at vocabularies. It has free RDF dumps and linked open data exports with all the bells and whistles. It has a public live Sparkle endpoint. And this is maybe the most important piece of technology that you have there based on Place Graph, and really a key asset to the whole community and to many third-party users. So many processes in the community these days rely on Sparkle as their information source. It's an incredible success, but also an incredible challenge. As data grows, Place Graph reaches its limits, and you may know that Place Graph has not been maintained for many years by the people who have originally created it, because Amazon has bought them up. And Wikimedia is now looking for alternative solutions, and it's not so easy to find open source solutions which are fully Sparkle compliant and do not interrupt the service and can scale to this size. Yeah? So there's definitely also challenges ahead, and we shouldn't take it for granted that semantic web has been successful and will always be the successful technology used here. But for now, it definitely is. Okay, so this is complex knowledge graphs, and we've seen many things are therefore using complex objects, and they turn them into triples. But how do we actually get back when we do this? And well, the first technology that has faced this problem was probably OWL, which has had an RDF syntax back in 2004 already, when people didn't have so complex knowledge graphs being used yet. And the kind of approach that it used can roughly be sketched like here. Yeah. So on the left-hand side, you have OWL RDF documents and maybe also a knowledge graph. This is usually called the A box in OWL. And to process this, you then feed this into a parser. And the parser does some specific things to it. Yeah. So usually it's the OWL API when we work with OWL to extract OWL objects from the triples. That's a custom process. It's a Java program in the end, but it's governed by a specification of W3C. Of course, it should be conforming to this specification. In the graphics here, the higher level, this is the heavenly sphere of the standards and working groups where great minds are working out how we should use technology. And in lower levels, these are the earthly realms of normal users who can specify things and actually work with the technologies given to them. Okay, and once you have the OWL objects, you can then feed them into a reasoner. Again, what you should do there is governed by a spec, but you can implement it in many ways, and then you get the results. Okay. Now, this is a great process and great for what it does, but unfortunately not always what we need. So because several reasons. First of all, ontological information may be intertwined with the knowledge graphs. This is something we see strongly in Wikidata. Just because it's data doesn't mean that there is no ontological information there. It's just not separated in the way that we used to do it in the past of the semantic web. Also, what reasoning we actually want may depend on context. It's not the case that in all cases, even if we could use OWL, we really want that. There's not always one right semantics for interpreting a graph. This already happens if you do simple kind of analysis, quality checks. For example, you want to make sure that there's no redundant information that you could also have inferred in your graph. Then you cannot use an OWL reasoner, because for an OWL reasoner, there's no distinction between explicitly stated and inferred information. Yeah? You need to have some other way of inspecting your data. And as a third point here, we may also need new semantic interpretations that have not been foreseen by any working group at W3C so far. And to give an example of this, you can just look at the very first item of Wikidata, Q1. This is the universe, which contains a statement of this form: universe has parts of the class astronomical object. So has parts of the class here is the name of a property, and it immediately strikes us as something ontological that is going on here. But it also could mean many things, right? What do we say here? Does it mean that everything in the universe must be an astronomical object? Or does it mean that all astronomical objects are part of the universe? Or does it mean that the universe has some parts that are astronomical objects? All these are different, logically speaking. But thankfully, there's documentation in Wikidata, and we can just look it up. So there's a page that describes all this and gives great lengthy detail in English and with many examples on how this should be interpreted. And if with some background in formal ontologies, when you read this, you come to the conclusion that what is meant here is that the universe has some parts that are astronomical objects. So if we wanted to express this in OWL, we would have to use this little graph here. So the universe is subject to an OWL restriction, which is a sum values from restriction on has part. So we could express that, but this interpretation step is not something that is standardized. It's something that we have to do for the specific application here. Okay, so how do we solve that? Well, the way in which this was solved in practice already since many years by practitioners is to use Sparkle. Right. So we have here a slightly different pipeline. On the left-hand side, you have now the knowledge graph with the ontology included as part of the data. And in addition, you have the Sparkle query, which tells us how to evaluate this data. And I have drawn a little star here, not just because it's called Sparkle, but also because some of this heavenly power of telling us which semantics we want to apply is now residing inside this query. And then we have a standard governed process for evaluating it and getting the right results. So for example, here is a little query that finds all cities. You probably have seen things like this. So we are looking for elements that have a type, which is either a city or is some subclass of cities. A little Kleiny star here tells us that we are looking for subclasses. And so we see that we have completely implemented the RDFS semantics of subclass of with this Sparkle query. No further reasoner needed. Okay, so this ticks all the boxes. We now have ontological information intertwined with the knowledge graph. We have reasoning that we can switch on or off or even mix within a single query. And it allows us to interpret any vocabulary we find in our graph in a semantic way using these features. Wonderful. Okay, so how far does that get us? Obviously, as you have just seen, well, it's not completely obvious, there's more to be done, but RDFS can actually be handled in this way. So you can implement the RDFS semantics fully in Sparkle, just using queries. The other things that I have listed here are different versions of OWL. So these are the lightweight fragments, QL, RL, EL, which have been created because they are supposedly easier to implement, and that's true in practice, than the full-blown OWL2DL. So we might also look at them and ask, can we implement their features, their semantics within Sparkle? And well, to some surprise, I would say, we actually can, at least for our QL. This is something we figured out in 2014. Also at this conference, here you see a little excerpt of one of the Sparkle query patterns that you need for that. Don't try to read it. It's awfully complicated. Essentially, it just finds empty classes, which is just one part of the reasoning process. And it's already quite lengthy and still uses some macros inside that you would have to expand to get a query from this. Okay. So it's complicated, but it can be done. Yeah. So encouraged by this, we might look further into OWL, but there we actually see that it's not possible. And there's direct ways to show this, but an easy way to see this immediately is to apply some complexity theory. OWL is known to be a polynomial time-complete language, whereas Sparkle query answering is in n-log space. And n-log space is widely believed to be strictly smaller. It's a subpolynomial class. It's even simpler than polynomial time. And so if we would be able to somehow express OWL in Sparkle, we would have made a major breakthrough in the field of complexity theory, which is frankly quite unlikely. As I said, there are direct ways of proving it's impossible, but it gives us good guidance. A little complexity theory can go a long way sometimes. EL is actually the same. It's also p-complete, and L2DL, okay, don't even mention it. It's n2x time complete, so we don't have a chance there. Right. So where do we get something more powerful than Sparkle if we want to have more semantics? Because obviously there are several communities that need more than just RQL and RDFS. Yeah. And well, the answer to this is fairly obvious. It has always been there. So this is a layer cake of 2001. And even there, we already had rules explicitly mentioned as one part of the semantic web, which is of some importance. And since then, rules were never really gone from our community, but frankly speaking, it was a quite complicated relationship, I think. Yeah. So there were many interesting approaches. Notation 3 logic of Tim Berners-Lee already had rules in it. There was the semantic web rule language swirl, the rule interchange format, which ran from 2005 to 2010 as a W3C working group. OWL itself, RL is for rule language. It was motivated by being expressible in rules. And more recently, also a renewed interest in rule languages outside of semantic web. So I mentioned here the first Datalog 2.0 workshop, which was an event mostly by the database community and knowledge representation communities also, that marks the renaissance that we have seen in the last decade of study of rule languages and practical application of rule languages. So there's a lot of things going on around rules. And all this time, I think semantic web practitioners have used various forms of rules, except RIF, I'm afraid. This hasn't really gotten much traction for reasons I'm not competent to explain to you. Maybe we can discuss it. Okay. But for this talk, let me just mention one very simple rule language and not spend much time on it. Datalog, you probably have heard of. It's a simple rule language where you can have predicate logic rules like the one shown here. If X is of type Y and Y is a subclass of sets and X is of type set. And you can apply these rules recursively, and this is where the whole power comes from. There's not much more to it. There's nothing complicated, no negation, no disjunctions, no built-ins or filters. All the bells and whistles you could have in other languages are not here. And there are fast reasoners, even fast reasoners with RDF support that you can have, which is maybe not surprising because there's polynomial time data complexity, so we would expect good scalability here. I mentioned here RDF-Ox and vlog because they both have direct native support for RDF data, but there are also many other reasoners that can be used with rules outside of our community. Okay. So what do we get from that? Actually, Datalog reaches a good bit further. So what I did here in the pipeline above is I replaced Sparkle now with Datalog and the Sparkle engine with a rule engine. The rest is mostly the same. And we can see that suddenly it's possible to also implement OWL and OWL. And importantly, notably, when I say implement, I really mean that there is a small rule set which completely captures the semantics of these ontology languages. So you may know that OWL, for example, was meant to be convertible into rules. So if you have an OWL axiom, you can always rewrite it as a rule. But this means that if you have an ontology with 1,000 axioms, you get 1,000 rules. What I do here is quite different. I here have a fixed set of Datalog rules for OWL, for example. And no matter how large your ontology is, it's part of the input data that these rules are getting, and they will produce all the results with this fixed set of rules. So that's slightly different. And how to do this has been subject to earlier papers. DL is still way too complex for Datalog. Now, Are these rules complicated, you may ask? Actually, not much. I just show some, for example, here. So if C is a subclass of D1 and C is also a subclass of D2, and if we have an intersection D12 of D1 and D2, then we should know that C is also a subclass of C intersection. So these are very simple rules that everybody can read and understand. The practical rules we use are only minimally larger than this. So that's quite simple. You may note here that is inter, of course, when I say there's an intersection in my ontology that describes the intersection of these two classes, this is not looking at all like triples. Yeah? So how do I get such a fact? I, of course, first have to extract this from the knowledge graph. And to do this, I should look at how it's encoded in OWL. So this here is a little graph shown, which gives the RDF encoding of an intersection. The red node here is an intersection of two nodes, blue node D1 and the other blue node D2. And now I would have to somehow extract the information that this intersection is there. And I can, again, use a rule to do that. Here it's slightly longer, actually, because I need all these triples to be involved. And then I can say, okay, under these conditions with this pattern, we get an intersection. Okay, excellent. So overall, this is not very complicated. It requires just 10 reasoning rules and about 36 parsing rules to do all or most of OWL EL. We had a tutorial on this. When I share the slides, you can look up the references if you're interested. Okay, so what have we accomplished? First of all, we have moved from ontologies to data. And we have moved from W3C semantics to user space semantics. So users have the full control over what they want to do with the data. They can still do it in a conforming way that follows the specification, or they can change something and do some new semantics, try something out which fits their application. And also we have moved from dedicated reasoners to less than 50 lines of code, which is also something. Now, all of this sounds a bit too good to be true. And of course, there are major downsides and difficulties one has to face. Well, first of all, you may have noticed that my rules are not talking about triples. They use predicates of higher arities. I used arity 3. It turns out if you want to support all of OWL EL, you actually need arity 4. If this can be proven, it's not possible to find any data log rule set that implements OWL EL without predicates of arity at least 4. So if your rule engine only supports triples, you just can't do it, sorry. Also, there's a major performance cost of this flexibility, of course. So if I take vlog and I apply this to our 50 rules here, or actually just to the 10 reasoning rules on the normalized version, I still need about 2 minutes to classify all of SNOMED, which is a big medical ontology that is often used for benchmarking. That's not so bad, actually, but it's not the state of the art. Yeah, so if you would take the ELG reasoner today, you would take 10 seconds for the same task. So it's like 2 orders of magnitude we pay in penalty for the flexibility. And finally, it should also be mentioned that getting rules right is really not easy. So it might just be 50 lines of code, but these are the 50 lines of code that people write research papers about. And it requires a lot of expertise to get a semantics implemented in this way without forgetting anything. Yeah? And we have many examples of this where people have forgotten something in the past, in even reviewed publications, but also in W3C standards. If you remember the RDFS reasoning rules, which were included in some early standards, they were not complete either because people just forgot about something. Yeah. So it's not so easy. And if this weren't enough, of course, we also have to acknowledge that data log in itself is not really enough to achieve everything we might want to achieve. Why is that? Well, 2 observations. First of all, encoding complex objects in RDF requires auxiliary nodes. This is something I have started with and to explain to you with many examples. We need B nodes or auxiliary nodes. I mean, it might not be blank nodes. Actually, we can use anything there to encode complex structures. But data log is not able to produce new auxiliary nodes. All it can do is to create relationships between nodes which we already have. So this is a major weakness. We can parse complex RDF structures, but we cannot create them with this framework. How is this fixable? Well, actually, the solution is not very difficult. All we have to add to our rule language is some facility to invent new values, to create new objects whenever we need them. For example, here's a rule which actually turns around the parsing of intersections from an OWL document, which I just showed you, by saying whenever I know that D12 is an intersection of D1 and D2, this should be represented as a structure of 5 triples. which involve two additional objects, N1 and N2. I write them here in the standard blank note notation to indicate that there's some new thing being created here, some unknown thing for which we have no further specification. In the literature, often we write existentially quantified variables in this place. And this is also why it's called existential rules, because we are saying here that a rule infers the existence of something. Yeah. Okay. So existential rules are actually still rather easy as a language, a very simple language, mostly like data logs. The only thing we add is this value invention, that a rule can produce something new. And this has been around for forever as well. I mean, even in notation 3 logic, you have this capacity of producing new elements, and it has been there in Swirl, it has been considered in Riff. So this is not a new idea. It's something that we always have taken into account. Unfortunately, doing this makes query answering undecidable. And intuitively, this is maybe not such a big surprise, because as soon as you start to create new objects, you increase the size of your database, and you can have more complex relationships between the new objects than the ones you had before. And this might happen in a way which is not easy, where it is not easy to detect that you are creating more and more new objects. So it might happen that applying rules in the normal feed-forward way that often is implemented in practice will never come to an end. It will not terminate. Nevertheless, fast reasoners with RDF support exist also for this fragment. So both RDF-Ox and vlog do support existential rules, so you can use them. And in some sense, it's still not so complicated to work with this logic, because there's still no negation, still no disjunction, and no built-ins or other features that we have seen in so many other rule languages. So it's still a very simple language in many ways. Okay, now, is there a contradiction here between undecidable and fast tool support? Well, of course there is in a way, and this is what I already said. The fast reasoners we see today, most of them at least still are based on applying rules in a feed-forward way and hoping that this will terminate. Of course, they don't just hope, they also try to avoid the creation of fresh elements as much as they can. So when they have a rule which says there exists a new, let's call it blank note, yeah, there are new elements that we need to satisfy something, they will not just blindly create it, but they will see if they maybe already have an element that can be used in this place, whether the rule maybe is already satisfied. Maybe there is already something, you don't have to create a new one all the time. Okay. There are other implementation techniques that have also been tried in practice, but the majority of tools I know of are going for this approach. And so it also means that the majority of tools that are available require termination in order to work in practice. They need rule sets that will at some point come to an end when you just apply rules. Okay. So what can we do with this fragment? What is the power of terminating existential rules? And for this, we can first recall here in the gray box what we know about data log. Data log cannot see any negative information. It has no negation. It cannot ask for the absence of a triple in the graph. And we also know that data log is polynomial, so it cannot solve non-polynomial tasks. It's restricted to this subspace, positive tasks in the polynomial time domain. For existential rules, we know by definition that they still cannot see negative information. There's still no negation. Nothing has changed there. Well, if we restrict our attention to terminating rules, we know that there is an implementation for this. And so we know that whatever we do there, it is at least computable. No? Okay, so this is a very high upper bound, right? So somewhere the power that we have must be between polynomial time data log and between everything that is computable without requiring checking the absence of something, intuitively speaking. Okay, and for quite a while, it has been unknown where exactly we are on this spectrum. Last year only, we were actually able to come up with a new result, which is somewhat surprising because it tells us that the true expressive power of these rules actually is the upper bound. So terminating existential rules can solve every computable task that does not depend on negative information. Okay, this is very hand-wavy. If you want to know the details, please see the paper. Does not depend on negative information, has a formal definition. Yeah, but what this means is that everything we could wish to compute can be described using data log with blank notes in the heads of rules. And that's quite significant and quite surprising too, because there are so many other things we could have added, right? Like disjunctions, for example. Apparently, we don't need disjunctions from a computability point of view, at least. Okay, right. So this is interesting, and it shows us what is possible. Now, I can see some of you, unfortunately, I can't see many of you, but I guess some of you might be skeptical right now, right? So like this fellow here, it's a wonderful photograph of the eminent mathematician Thoralf Skolem, who looks as if he has some doubts at this point, because yes, I'm working with blank notes here. And of course, we all know that blank notes are bad, right? Nobody likes blank notes. Linked open data enthusiasts do not like blank notes. Ontologists and description logicians do not like blank notes at all. And even practitioners do not like blank notes. In fact, Wikidata just eliminated all blank notes from its RDF exports earlier this year. Yeah? So why in the world do we want blank notes? Can't we get away with something less general? Can't we just, create new names for the things we introduce, some fresh constants, instead of making them blank notes? And well, the answer to this is actually we can. And but we have to be very careful. So one standard way of getting rid of existentials in logic, and this is why this fellow is shown here on the slide, is to apply a technique known as Skolemization after this Mr. Skolem here, where you basically create a new IRI for an element based on the parameters that went into its creation. Yeah? So if you apply a rule, you know what parameters the rule was applied to, and these parameters you use to mint a new IRI. And this is called Skolemization, and you can do that. But you have to be careful that your rule engine should not rely on the shape of the IRI for when it checks whether a rule is redundant or should be applied. Yeah. Because if you only rely on the shape of the IRI, if you just syntactically compare your new constants to what you already had in order to decide whether you need to create a new one, then it is known that the computational power of your formalism drops all the way down to data log. Right? So that's somewhat surprising, but it is what happens. So if you Skolemize, as we say, existential rules, and you restrict yourself to cases where you have guaranteed termination, then all you can express is the same things that you could already do in data log. And all the complications with the blank notes are somewhat in vain. They just make things harder to read in a certain sense. Yeah, so one has to be careful. But of course, we could still, after applying the rule engine, after checking if a rule was applicable, we are still free to replace the blank notes in our data sets and get rid of them if we don't like them. So I'm not an enthusiast for blank notes either. Okay, right. So let me summarize what we have learned and discuss a bit what it means. Yeah, so I have introduced a pipeline, which I think is useful in practice, where we take a knowledge graph that has ontological information and combine it with a user level specification that is formal and shareable, and then apply a rule engine maybe or some other engine to obtain results. And hopefully there's some standard governing how this should be done. For data log, certainly there are standards that we could apply. RIF also has a data log semantics that one can refer to. And if we do this, and if we add some features, we can really implement any ontology with this, at least in theory. I have added here in this list, not just data log, but also the version of data log you get when you restrict yourself to triples in your rules without value invention, just inferring new triples from existing ones. It turns out you can't do more than Sparkle. These languages are still very different from each other. So Sparkle can do many things data log cannot, and vice versa. So don't be fooled by the fact that the two columns look the same. It's just for these two cases that they happen to have the same power. Data log can do more, existential rules can do anything. And okay, this is merely theoretical, of course. I wouldn't want to implement an LDL reasoner in existential rules. It will not have any chance of scaling very well. It's just principal expressive power so far. But what it does is it shows us what is possible. It shows us that it is possible to have completely declarative specifications that capture all the complexities, all the things that we have in our current semantic web standards. Now, you might have some confusion here as well, because of course we all know that LDL has negation as a feature. And I just said that we cannot use negation in our rules. Yeah? We don't have negative information. But the reason why this is still possible is that the OWL negation is an open world feature. Yeah? So we have open world semantics, meaning that negation is only applied explicitly. Whenever we have negation, it's an extra feature that we can detect from the patterns in our graph. It's never the absence of something. It's not negation of failure. And this is why existential rules already are enough in principle to compute this. Right. So that's a technical summary of what I just told you. But it's not the summary of my talk. I want to have another summary with what I think really matters. Yeah? So I wanted to give you some theory as well, because as you have heard initially, I'm at an Institute of Theoretical Computer Science, so I should better live up to that. But I also want to keep in mind the bigger picture that we have for the semantic web. What I told you essentially is this. We have split the world into triples, but we still struggle to put it back together, with which I mean that we have a lot of expertise in encoding data in RDF, and we do this a lot, but we have very limited technologies and also limited tool support, to be honest, for reassembling the complexity that we have atomized in this way. Sparkle is a start, but it is limited. It cannot capture all the meaning that there is in the graphs that we already see today. Of course, there are also scalability limits even to Sparkle, yeah, if we have large graphs. Rules are powerful, but also subtle. Tiny changes in how you define a rule language can make big changes in expressive power, as we have seen with Mr. Skolem there. Also, designing rules is not so easy. One has to be very careful. And so this is also an argument for making things shareable. Because if you have a way of sharing your knowledge, you can design the rules once and then upload them somewhere, and other people can use it like a library, like a module, instead of having to come up with their own EL implementation, for example. Okay, so this is my first summary. The second important point, which I think I should make here, is that in my view, the era of standard semantics has ended. It's a bit of a strong statement, but I will relativize it further. Well, real-world complexity, as we see it now with all the successful applications that we have in the semantic web, eludes single triples and it eludes single OWL axioms. You can't just have a spec with a few possible cases that covers all things that people want to do in practice. We have already at this conference, you will see many interesting things that you can do with data that is simply not possible, and making a new standard also takes a lot of time. Also, our needs change from context to context. There's no one ontology language to rule them all. There is always a back and forth, and sometimes we need to switch something on and something else off. We see this all the time, not just with OWL. Also, if you talk about reification, if you talk about things like referential opacity, which is a topic in the RDF star community, for example, where you have the need to distinguish between what is stated and what you know as an outsider about the things that are stated. And also, I think truly managing knowledge requires more than one AI method. So it's not just about different formalisms for reasoning. It's also about bringing together different technologies, but not just in some ad hoc way, but in some principled way that is understood and that leads to trustworthy and reliable applications. And I think this is the challenge, right? It's always easy to just throw a bunch of scripts at a large data sets. And this is often what even we do these days because of the lack of technologies to otherwise process the data. But I think it's not what we want to do in 10 years from now. Okay, so standard semantics has ended, but at the same time, declarative, shareable meaning is more relevant than ever. And I found it very telling, again, to hear some of the discussions at this conference, including yesterday's panel, that there's so much questioning of our own relevance in the whole ecosystem of modern information technology with AI and machine learning and data-driven techniques coming to the fore. But isn't it that this development is actually showing how important, how relevant what we are doing currently is, yes? So explanation and accountability requires shared concepts. And I don't mean shared like interoperable between computer systems. I mean shared as in shared between humans. We have learned in the last decade that trusting computers to decide what is true and what is false, or what to recommend us in our feed and what to hide from us in our social network is maybe not the right way to go. We need people who discuss about what we want and who can somehow encode their decisions, their human views into a system. And this only will then be able to get back to the human level. Declarativity also is key to interoperability and scalability. Even if you don't care about humans at all, the database community also loves declarativity because it allows you to have a process, an algorithm, a specifications that you can use on your laptop and then deploy on a compute cluster with thousands of CPUs. This is what you need declarativity for, to be independent of the underlying platform and implementation. And this is what you need for scalability. And yes, finally, knowledge is human. It will not go away. So no matter how good data-driven techniques are, they are not replacing the social constructs that we call knowledge. Yes, so there's always a need to discuss and to agree together and to reach out to the human consumer if technology is supposed to be meaningful. And I think we can also see this when we look at Wikidata, for example. I mean, Wikidata has a large community, but the community is not just thousands of data entry clerks who are, working 24/7 to type fast many statements, but rather this community is a community of conceptual modelers, of people who discuss how can this complex thing that we perceive as the world be captured within a fixed structure. And this kind of discussion you can see if you go to the community chat page on Wikidata, for example, and you can realize easily after a few posts that you read there that this is way beyond anything that a machine learning tool will be able to do. Yeah? You first have to have the discussion, you first have to decide how to model, and then you can use tools like machine learning, like information extraction, like alignment tools, and so on, all the important things that we are also working on. But you first have to make a decision what you want and how to represent it. Okay, so what's next for the semantic web? So the yellow box summarizes my main thesis here, and the question now is what shall we do about it? And I think the first thing we need to do is we need to appreciate what we as semantic web community actually stand for, what it is that we bring to the table and how our contribution is absolutely essential for taking forward what the current digitization and computization movement all around the world is doing to human lives, to societies, and so on. Yeah. And if we want to understand what we stand for, I think it's completely misleading to look at diagrams like this. Yeah. So this stack is a mere technology stack created in the early 2000s, which does not take into account the ecosystem that it's based in. And the key thing here is not, URI or XML or RDF or ontologies. Not even the triple is key for the semantic web. The key for the semantic web is the community that somehow comes together and that builds this, that agrees on this knowledge and that builds these things. And this, I think, is the true meaning of semantic as opposed to just data structure. And this is what sets us apart from logic communities, from database communities, that we have this intrinsic idea that what we model is knowledge and not just data. Okay, and from there, we can then continue to spread our values, to explain to other people that clear meaning, sharing of information, precision in doing so is incredibly important, that we need flexibility, scalability, and collaboration, and tackle these as big challenges, and to find new ways of agreeing on these standards. So I put standards in quotes here because I was arguing for flexibility, but I don't want a wild west of incompatible ways of approaching data, but rather I would like to see something where people discuss these and also share them in an agreed way. Yeah. So these are some points to move forward, and I think my time is over. So I thank you very much for your patience, and end with this slogan and picture, and looking forward to your questions. Thank you very much.
Okay, maybe some virtual applause. Thanks very much for the fantastic talk. Particularly appreciate the very positive message at the end, which I think is a very important one, and which resonated with me, and I think with other people in the audience, that our topics are relevant. It's almost too motivating. I almost wanted to leave the keynote to go work in these topics, but I managed to stay here.
Stay for 10 minutes.
So there's some questions in the chat. I'll invite Axel, if you could raise your hand and maybe you could ask the question yourself. while you're doing that, I can also share the joke of, I like blank notes. Some of my best friends are blank notes. It's a very old school cut from the old folk days when everybody said they knew blank notes.
Right.
So Axel, are you joining? I can read it for Axel then. So I have a more serious question. Blank notes also have some positive features relating to scoping, the locality of blank notes. So Axel considers that to be a feature rather than a bug. So do you have any thoughts about that?
Yes, that's true. I think there is a utility in having blank notes, and I do think that, I mean, what essentially blank notes are semantically is existentially quantified variables that scope over the whole knowledge graph. That's not a good or a bad thing. This is just what they are, and it can be useful in applications. I think they are simply notoriously hard to handle for practitioners, and I think this is why people don't like them. Logicians don't like them because this overarching existential quantification messes up reasoning, it messes up your semantics, and makes it harder to do certain things. And practitioners often struggle to do the right thing with blank notes. Frankly, I didn't always quite understand what the key problems are in each case, but it's certainly clear that when you work with Sparkle, where you have a built-in semantics of blank notes that doesn't reliably allow you to retrieve them, for example, it is quite cumbersome. Yeah, so it's a blank note which is always treated as a blank note, I think is problematic. It would be nice to somehow just have the syntactic view of blank notes from time to time. And this is all in line with the flexibility I was arguing for. Yeah.
Yep. Fabian has a question. Maybe you could raise your hand. We can invite you to join, to ask the question. Hello?
He's coming.
Okay. So you can raise your hand if you put a question in the chat. Also feel free to just raise your hand without putting the question in the chat, and we'll invite you to speak your question. If you prefer, you can also ask in the chat. Fabian.
Yep, can you hear me?
Yes.
Yep.
Okay, excellent talk. That was, I mean, I completely agree with Aidan. I could have listened to you for 1 more hour. It was excellent. And I'm really happy also to have this topic of rules being discussed both technically and with this vision. I have a very simple questions. You touched on the question of the fragments, profiles, RDFS, RLRL, and so on. The current W3C standard, they have sort of established a fixed list of such profiles and fragments. When you talk about flexibility, are you pushing us to go toward an open list of profiles? Should we open that list, be more flexible in our approach to a profile up to the point we can negotiate the profiles of the agent to which we are talking? Is it something you would consider?
Yes, I think, I mean, when you say open list of profiles, of course, using the term profile suggests that it's still the W3C profiles. I think having an open shareable library of queries or of rule sets that accomplish certain goals is already very valuable. And this is something, for example, the Wikidata community does that all the time. They have shared queries. They even have distribution of work when creating queries. So there's help pages where people can ask informally a query that they would like to have answered, and other people who are experts are then working out how to get this done in Wikidata. Because this requires a lot of understanding also of the structure underlying the knowledge graph, not just of Sparkle. And one could do similar things with rules as well. Yes, well, we could have pre-created rule sets or rule sets agreed upon by experts, and then, you know, approved and stamped and ready for use in whatever application you need them. And I can imagine this to be in the form of profiles, where you have some feature enabled and another one removed because you just don't need it. It can also be in the form of different semantics. Yeah, profiles are always parts of one large semantic. But for example, this morning we had a great, interesting talk on the standpoint logic approach, where you have different standpoints of people that you can compare. And this would be completely useful and valid and valuable for something like Wikidata, where we have so many different sources that represent different standpoints. So we might want to reason with standpoint logic, but that's not a profile of OWL or first order logic in a direct way, but it's a different logical paradigm. But we might still be able to implement it in a fixed set of rules and then use this. And yes, I think there would be big value in sharing these, in having them interoperable at some point, and not just creating them locally. I think this is a point where maybe I should also comment on. For our ontologies, we see that people are sharing the ontologies, and for rules, we don't see that. Even though we have the riff as a, it's a syntax, it's not the best, maybe it's not the worst, it's something that actually can be used, but still nobody shares rules. And if you go to the industry, if you ask people in startups, then they say, the industry is not really interested so much in shareable syntax. They want, connection to their ERP system rather. So why is that? I think the special thing, the unusual thing that we have to ask here is not why is nobody sharing rules. The special thing we should ask is, why have people ever started to share ontologies? What made people collaborate in this way? It's not necessarily what business wants. And I think finding people who want to collaborate, who want to share things, as we usually do in the semantic web, I think this is important to get this working.
Okay, thank you. So Wojtek, are you with us? Would you like to speak out your question? If not, so regarding your final message, do you think we should put more effort into mapping our ontologies to other communities' data representations without insisting on going through the RDF data layer, even to more distant ones than Wikidata?
I think we should map, yes. I mean, definitely this is a good thing. I'm not sure about insisting or not insisting. I mean, for me, this is all technology, and there are good uses of technology and bad uses of technology. RDF is great, and I think it has achieved many things that you wouldn't have achieved with other technologies. And even though I have showed some reasons to find triples also a challenge, I think triples are also really great. They really enable many things that we couldn't have done in other ways. But I think it's misleading when we convince ourselves that the world is triples. We have to be aware that we are making it into triples by normalizing. I once was a co-author of a paper where we proposed OWL LD, the single triple fragment of OWL, to say, okay, we should restrict ourselves to OWL axioms which only need one triple to be written. I think this is the wrong way, right, today, I would say, because it says what people want to model should follow the technical format. I think it's the other way around, right? We should somehow continue using triples, but we should find ways to support people who need more than triples and not just dismiss it and say, okay, you're doing it wrong because it's not just a triple.
Yep. Okay. So we're at time, but I propose we continue for a few more minutes until 10:05 and to give space as well before the next session. But if people want to leave now, there's a problem. But so there's a question from Claudia. I guess you can speak it, Claudia.
Yes, thank you, Markus, for the great talk. It was really wonderful to hear you. My statement, my question is actually related to one of your last statement, in which you declared that managing knowledge requires more than one AI method, and this seems to me related to fairness, which is one of the key point with the AI method, AI and ethics, which has been also argued yesterday during our first keynote. Is it, in your view, the time for this community to start focusing on fairness more deeply? I mean, is it just a coincidence that this aspect rise twice during this conference? And actually, fairness is something that we mentioned, we somehow takes into account, but it is not a key point, as for instance is becoming in the whole AI. So is it, in your view, something that we need to focus on more deeply?
Yes, I mean, this is something I think whether we need to or not, I think it's definitely an opportunity to bring this into our community more strongly as well. I think something where we are very strong in as Semantic Web is to make the bridge between the informal and societal, even the community idea, and the technology. So we never are only social, we are never only technological, but somehow we make the connection, and we are striving to make formal, explicit technologies that can really support people by interpreting meaning in the same way that humans would. Yeah, and the question, I think, is completely open how to do this for fairness. So I think many important discussions are being had for fairness in the AI space, but also many discussions are staying completely on the informal level. There is often a lot of messages of community processes, of organizational processes that you should take away from this. But it's, maybe it's something that intrinsically, of course, you cannot measure fairness. You cannot make it a single mathematical concept in such a simple way. But of course, there are ways to formalize aspects of it. And this is also done, of course, by the way. But I think our community might have a strong contribution in encoding this in an actionable way. Yeah? So to think about how can we actually formalize our ideas of what fairness is in a way that can be acted upon. And as you said, yes, requiring more than one AI method here to come together, this would be a prime example, because fairness mostly applies to techniques which are uncontrollable and somewhat opaque, like the data-driven things where we just infer something and we need to have extra measures to trust it, much less so for the knowledge-based technologies that we often are working with. And I think bringing these two worlds together is a major to do for the next decade. Also in semantic web, we are also in Dresden working on these topics, which we call composite AI. In other places, I have heard the name bilateral AI. Sometimes hybrid AI is also used for this. So I think this is really where the future of AI is, to bring knowledge and sub-symbolic message things together. And I will be happy to work on this as well. So if anybody here is inspired and wants to work in Dresden, you can always talk to me. I will find something.
Thank you very much.
Okay, thank you. Axel, you have your hand raised. Not sure if it was from before.
If there's still time, just a quick one. I think the idea of this sharing rule sets is very appealing, but needs a standard of sharing rule sets. You mentioned RIF. It's not, I think one of the reasons why RIF did not become successful is particularly because it did not advocate a simple way to share rules like data log or like rules, but this would go too far. Where I wanted to go at was, for instance, for things like Wikidata, I think this would be super interesting. Do you see a way of doing this, particularly also in the way that Wikidata is modeling the kind of the ontological statements, so the T-box differently in a way, right? So you have basically an evolving ontology language within Wikidata, if you could say, because somebody could add new subclass of relationships or whatever variations of etc.
Yes.
I know this goes far, but
yeah. I mean, yes. I mean, yes to both. I think so. As to the evolving ontology language, I mean, this is where Wikidata is a prime example. We actually, when I was planning for Wikidata together with the team, Danny Frandicic and others back in Berlin 10.5 years ago, I was still advocating more explicit ontology, and I kind of lost the fight towards this. And maybe this is all good from today from today's viewpoint on, because it would never have sufficed for what we need now in practice. But Wikidata is a prime example, not just of moving targets in terms of modeling, but also of the requirement to extract from the big thing. You cannot take all of Wikidata and make a coherent logical theory of it. This will never work. You have to focus on something, take some vocabulary, take some viewpoint, some perspective, and make some meaningful model over it and improve the data based on this understanding. But then you may zoom out again and go into some other detail. And I think for this, rules can be used, and I think sharing them, even RIF, I mean, we have the basic logic dialect, and I think with good libraries, you could hide much of the difficulties that are in there and make it as a data log transfer language for people. I think the reason why it's not used are maybe different reasons altogether. I think it's really the need that people want to share these rules is not strong enough. And to be honest, I have to say, we are still struggling too much with scalability. The data is growing faster than our processing pipelines can keep up. Even Sparkle, as I said, is a challenge, and not all but certain that we will have Sparkle in 5 years from now if nothing big happens there. And rules are even more difficult. So even if I would have rules that describe something meaningful on Wikidata, I wouldn't currently have a tool which is able to take all of Wikidata in and apply them. And without this tool, of course, there's not much incentive for users to do it. So this is where research is needed, where the community needs to do something to provide solutions that can actually show the benefit of this and not just work in theory.
Okay, we were out of time, I guess, to not steal attendees from the first talk of the next session. I guess we better conclude. There's one maybe yes, no question. Do you like N3 for sharing rules from Thomas in the chat? N3, yes, no?
I should say no, because I don't know it enough to like it, but okay. I'm open to it and I'm looking into it. We have colleagues here in Dresden also looking into N3 rules, and yeah, it's an interesting approach too. I mean, I think there can be something getting out of this. Yeah.
Okay, so we better conclude, but there is a Slack channel for the keynote. If people have questions, Markus, please do check out that Slack channel and see what questions emerge there.
Just drop me an email, send me a Slack message, whatever. Yeah.
Perfect. Yeah. And in the chat, there's a link to the next session. So a virtual applause again. This was a really great talk. So next up, there is a technical session. So there will be talks from the main tracks and from the industry track, I believe. Sorry, I don't have the program, but so there will be talks again. So there's 2 minutes left to that. So please rush, get there. Thanks once again, Markus. It's really great talk.
Thanks for having me. Bye.
Okay.
Thank you. I'm closing the session.